Okay, so yeah, we've got a lot of people. We've got a lot of people coming in a little bit late. So what I'd like to do now is prove. We're going to take a look at another heuristic.
No questions?
Oh, actually, I'll tell you what. Because this is not a day that the homework is due, let me postpone the questions until later in the lecture, because there's some material that I want to go over, and then I'll before class is out, I'll ask for questions. Okay? Because the homework's not due until the next time. So, and because I think your questions are going to be over material that we're going to cover.
Okay.
So let's just make that at the end.
Start on the homework. Yeah, that's nice.
I did, and you are really good. It's really good that you did start on the homework ahead of time.
Yay.
You are to be commended.
Double the class size.
All right. Now, so we're going to illustrate this next heuristic. What I would like for us to do is to prove that P or true equivalence true. Which one is that?
Where's my green pen?
3.29.
Okay, so here we have here we have the axioms and the theorems for disjunction. So disjunction is the OR. And look at all these axioms, man. We've got the symmetry of OR, so P or Q equivalents Q or P. We've got associativity of OR, so P or Q first and then OR that with R is the same thing as ORing Q and R and then ORing P with that, okay? We've got the idempotency. Oh, this is an interesting one, idempotency. The idempotent property says P or P equivalents P. Now, this is really not, you're probably not familiar with this one at all from algebra, because it's not the case that A plus A equals A, right? That's bogus. And nor does it work for times. A times A equals A. See? So none of these are true. All right? So here, right? That's not true in algebra, but what the heck? It's true with disjunction. P or P equivalents P. And so that idempotent property is a property of disjunction. 3.27. 3.27 is interesting. It says that OR distributes over equivalents. And so it says if you have P or and then parentheses Q equivalents R, that's the same thing as P or Q equivalents P or R. Now, the analogy here is how multiply distributes over addition. For example, in algebra, if you say A times B plus C, what did you learn in algebra that this is the same thing as?
AB plus AC.
Yeah, this is AB plus AC, right? A times B plus A times C, right? So that's the distributive. So this is a distributive, but it's really weird, right? Because it's P or Q equivalents R, right? So what's funny is that here, here this is a plus, but here this is equivalents. But what this is saying is it's the same thing as what? It's the same thing as P or Q. P or Q equivalents P or R. Now, and so these two things equivalent, right? It's kind of strange but true. And the next axiom is this axiom called excluded middle. And what that says, the excluded middle says P or not P. Now what's really, here's the thing that people get a little confused about when they see this for the first time. This just says P or not P.
Either it's true or it's not.
Well, because this is a theorem, it's true in all states.
Right, yeah.
He was
Okay,
explaining.
but Yeah, but I mean, here's what's interesting about this. A lot of these ones that come before have equivalence in them, right? It's this equals this. Actually, do all of them have equivalence?
No.
Equivalence, 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 equivalence. True is about the only one, yeah. See, these all have equivalence in them. Yeah, true is a little unusual. It doesn't. This is the second one that doesn't have an equivalence in it. So, but we saw before that if you want to, you could say the equivalence true, right? So we saw before that any one of that equivalence true is redundant. And so if you want to think of this way, you can. All right? And because all theorems are equivalent to each other, anytime you have a p equivalence, or anytime you have anything or not the same thing, you can use excluded middle to just make that true.
So anytime you have.
Yeah, like suppose you're coming down here. Suppose you're coming in here, blah 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 blah, and you have maybe like p or not p equivalence q or I don't know some other.
Blah, 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 blah.
Yeah, blah, 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 blah. All right? What I'm saying is that you can do this. You can say equals by
Exclude the middle.
excluded middle. True equivalence q or blah, blah, blah. Right? What I'm saying is that anytime you have this, because it's a theorem, you can just make this true. Actually, after you have true equivalence this, what could you do for the next step? True equivalence. What could you do for the next step? What is true equivalence? Which one was that? True equivalence.
I remember that.
Q.
True. Yeah. Look at this is 3.3. True equivalence q equivalence q. So true equivalence this must equivalent what? This.
Same thing.
Yeah.
Yeah. So you could say by 3.3 q or blah 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 blah. Does everybody see how to use the excluded middle there?
Yeah.
So now we're
And you can just prove P or not P using a truth table. I mean,
yeah now
you
okay.
can't prove it, but I mean, like we know.
Yeah, we do know. In fact, every single, I guarantee you, I will give you an A in the course if you could find one of these theorems that if you do it a truth table, I guarantee you that that if you do all the possibilities, you'll have true in every column. Every single one of these theorems and axioms. I'll guarantee it. And if you find one where that's not the case, I'll give you an A in the course. Don't try it. Because you'll waste.
I tried the golden rule, and that one, I was like, this is going to take longer than 15 minutes.
Yeah, the truth table for the golden rule? Yeah, yeah. But anyway, so this is, all right, now I want to, let's prove this, this other one after the, let's prove this 0 of or, p or true equivalence true. Let's prove that. Okay, now, here's what we're going to do from now on. Instead of me just asking in general and having everybody kind of like answer out, the question, we'll go around the room. Okay? So,
Sounds like fun.
it is fun. So let's prove 3.29. 3.29, and what we're trying to prove is P or true equivalence true. P or true equivalence true. Okay, so I'll get you started. Okay, so what we're going to do is this is equals, equivalence. So we're going to start with this side and get it to this side. Are you with me?
Yeah.
Okay, so here we go. P or true equals. Okay, what do you think, Ben? What should we use on this step? How can we get from, how can we do this? This might not be too obvious out of what we need to do here.
I got it.
Hold on. We're going to go around the room. You'll get your chance. You'll have your turn. Can you think? I'll give you a hint. I think what we need to do is with this true, we need to change this true to something, no, change it to false. No, we need to change this true. We need to substitute equals for equals on this true. Actually, it's not on this page. Let me get. Yeah, it's on here. It's, get your equation sheet out, right?
Do that. All right.
Do you see a?
I was going to do 3.3.
Actually, even before that, yeah.
3.3.
Ah.
Or 3.5. But, well,
Let's do. Okay, I tell you what. Let's do 3. Okay, so we'll do. So we'll say 3.3, and if we use 3.3, then what will this be?
well, where Q gets P.
All right.
You want them all to be P's?
You don't have to say that.
Yeah, yeah.
You don't have to take that.
Okay.
I just,
Good.
So it'd be P or P equals P.
Good.
We don't have to put in the subtool.
When it's obvious, you know. But sometimes for your own benefit, it's helpful to put it in. Not only is sometimes for your own benefit is it helpful to put it in, but sometimes it's helpful to put it in and then write it out in the hint so that you can see it. Because sometimes when you see it written down, it's obvious what you have to substitute equals for equals and going from here to here. You see what I mean?
You don't even need to make it P. You could just leave it as Q and still.
Well, no, I think we want it like this because watch what's going to happen in the next step. Okay, Rochelle. Now, what do you think we should? Let's go back to our new ones with or. Now, when you see this, P or parentheses something equals something. Now, what was one of the theorems that axioms that we just learned? You see P or what's the pattern? A little pattern recognition here. P or and then parentheses P equals P. Which ones did? Say it again.
Can you just repeat the order?
Why not? You sure can. And which one is that?
Um, 3.25.
3.2.
Okay. Yeah, I was just looking for the parentheses and things. Yeah, 7.
3.27. Okay, so 3.27 makes it what?
P or P equals P or P.
Right. Okay. So Kyle, what do you think? Now what are we trying to get this to? We're over here and we're trying to get it to here.
So true.
Yeah, actually this is true.
3.3.
Oh, your name's not Kyle.
Yeah.
Okay, so all right. So which one is it?
Apparently 3.3.
Well, do you see what 3.3 is there?
Oh yeah.
I was saying P or true or P.
Oh, what is here? Let's write down. Tell me. Can you quote what 3.3 is? What is 3.3?
True equals.
Equals
Just say
Kyle.
No.
with you want Kyle to say
Q
Q
replaced by
Q gets
P
P
or
or
P
P.
Yeah, 3.3 with Q replaced by P or P. Okay, so if you look at 3.3, if you look at 3.3 and everywhere there's a Q, do it's P or P, then what is 3.3? You can actually write this out.
True equals P or P equals P or P.
Yes. True equals P or P equals P or P.
question.
So, hold on. So therefore, we're substituting this P or P equals true, so that's true. And sure enough, we got it from here. We got it from this side to this side. Boom, we're done. Is everybody clear? Yeah.
Could you have done that last step differently and been like, oh, that's reflexive? And
Actually,
that meta theorem, then reflexive is also true?
well, hold on. You could not, okay, the answer is no. You can't stop just right here and say, oh, this is reflexivity. because we're not trying to get this to a previously proved theorem. We're trying to get it to true.
No,
I mean,
I'm
we're trying to get the left-hand
saying
side to the
it
right-hand
already
side.
Is, so, and since you know all theorems
Are true, yeah.
not equal to each other, and then
And
all
it's,
theorems is true.
it's true, but that's exactly what we're doing here. That's what
I mean,
we're saying here.
Could you quote it differently and be like,
Well, yeah, you could. You could. But what I'm saying is it's more straightforward just to have it look like this, yeah.
Could you read it like, well, I mean, like you do the exact same thing, but couldn't you re-insert the true at the top, at the bottom, and then just say 3.3 again?
Yeah, but you know, then you'd have equivalence true, equivalence true, equivalence true.
No,
Yeah,
but
so, and we
just have
don't like that
equivalence
style.
At the top and then put it in at the bottom, like whenever you're done.
No.
No.
Actually, I counted off one of the things that I commented on one of your proofs that I gave back is you had a tendency to use the whole thing, but then use the principle that says you're getting the left-hand side to the right-hand side, but then when you halfway down, all of a sudden the right-hand side appeared again. We should talk about that offline sometime.
Offline.
Well, I mean,
no,
if you want to.
Was that just on my last one?
Yeah, the one I just handed back.
No, I mean like the last 3.19.
I don't
I think
remember.
that's the only, well, like I counted off the first one.
Okay.
Well, anyway, yeah, I'm not sure. Okay, now, but before we go on, there's a principle here. Now watch this. Does everybody understand? Does everybody understand that what we did is we went from one side, from this side, we started with this side, and we got it from this side. Now, does everybody understand that we could have started with this side and gotten it to this side? In other words, we could have up here started with true. Now, but hold on. But now watch what this would look like.
It would look bad.
It would look terrible.
Watch what this would look like. It would look like this.
It's easier.
Now check this out. It would be true, identity 3.3, P or P equals P or P.
Yeah.
I mean, how in the heck would you go from here to here? How in the heck would you know to go from here to here?
You guess.
Well, I mean, you would.
Where'd you say
You
you
did
used
but
it?
backwards.
I know.
If you're gonna go from true to P or P equals P or P, you've already technically in your head gone from P or true to true.
Well,
You know the exact concept.
maybe, yeah. Okay, but anyway, this
Kind
is.
of a random jump.
It is kind of a random jump. As a matter of fact, this observation actually has, or this way of doing it actually has a name.
The random
It's called pulling a rabbit. Pulling a rabbit
Out of the
Out
hat.
of the-
out of a hat. And the reason it's called pulling a rabbit, it's like a magician. You know, here's a hat. Oh, here's the rabbit. You know, pulling. Where did that come from? Well, it's like it came from out of no. I mean, all of a sudden there's. So here's true. Pulling a rabbit. Well, now you got a P or P equals P or P. How did you know to go true for P or? You know, you're making it more complicated. You see what I mean? So here's the principle.
Don't do that.
The principle is structure proofs to minimize the number of rabbits pulled out of a hat. So this is a real principle.
Very sad.
Make each step seem obvious based on the structure of the expression and the goal of the manipulation. So, no. This is a heuristic. This is a principle.
Question.
3.34.
Question.
Question.
Anything that like equivalence true, like that way, you could just use 3.4 and then say it's true. You know what I'm saying?
No.
Because
I don't know what you're
true
saying.
is proof.
3.4 is true.
Yeah, 3.4 is true. So if you start with true, then you're done.
Yeah, but look, we are not getting this whole thing. There's a subtle difference here because we're not getting this whole thing to true. We're only getting this. We have to get this.
I know, but if
We
you
don't-
start-
we don't
if
get
you
this
start
to-
with the other side. If you start with true, then you can't do anything. Like, because you could just use 3.4 and be like,
No.
No, you
No,
can't.
if
You
you
can't
start-
assume.
Exactly,
You can't assume
yeah.
what you're trying to prove.
Exactly.
That
That's why
answers
you
my
can't
question.
do it. That's why you can't.
If
All
you
right.
start with true, then you have to get it to P or true. You can't just.
If you start with true, you'd have to get it to P. Well,
But I mean, if you start with true, then that's already like a proven theorem.
I'm gonna ask my question right
It's
now.
already
because
3.4.
Okay.
So you can't start with
All
it
right.
because that doesn't make any
So
sense.
my
All right, question.
the homework was, if you start with one side, can you just turn that one side into a theorem?
No, you cannot in general. That worked in this case, but that was a coincidence because true happened to be a theorem, a
Yes.
previously proved theorem. When you if you start with one
It
side,
has to be exactly.
it has to be, you have to get it to exactly the other side, which may or may not itself be, well actually I'll say this, which will probably not be a theorem by itself.
Yes. Okay.
So the answer is you can't do that in general. All right, is everybody good here? Okay, every once in a while I like to do a little, I found this little humor, okay? Check this out.
Doesn't make any sense.
Here's axiom, excluded middle. What is the excluded middle axiom? P or not P. I ran across this cartoon and I thought, whoa, that's excluded middle. Because what does he put on the door? What does he put on the door? Enter or exit only. Isn't that excluded middle? Because it's got to be either P, it's either true or false. Well, I mean, can't you see the connection? I thought that was a pretty slick. I thought that was a pretty slick connection. Isn't what he put on the door basically excluded middle?
Well, wouldn't excluded middle be enter or don't enter?
Well, I suppose it would, but exit is don't enter.
No, exit is coming
No, we
out.
can-
Okay,
No, we
man,
can-
you guys.
Not P.
Okay, well, yeah, I thought it was clever.
Thank you. Ben thought it was clever. Thank you.
Does not equal valence.
Oh my goodness.
That makes it exit.
Okay, this is going to be a good year. I'm not going to have any. I'm not going to.
Door.
I'm not going to have any problem getting discussion in this group. I can see. All right.
Talk as much as in this class.
So now you are going to prove for next time. You're going to prove the identity of OR, distributivity of OR over OR, and P or Q equivals P or not Q equivals P.
P or.
So those 330, 331, and 332 are assigned.
Wait, we have to prove that entire string on distributive of over 4?
Yeah.
Yeah,
It's
this
actually
one,
really, really
this
easy.
one,
That
and
was
this
easy.
one.
It's like 2 lines.
This one, I think what you should do is start with one side and get it to the other.
Yeah.
I don't know why you didn't start.
By the way, here's a little rule that will help you minimize pulling a rabbit out of a hat. Basically, the reason that we didn't pull a rabbit out of a hat so much when we did this proof the first time is because we decided to start with the more complicated side and get it to the simpler side. Do you understand what I'm saying?
That's a rule, isn't it?
That's a heuristic. That is a heuristic. And if you do that, if you have something equals something else, it's always easier to have something that's really long and work on it to make it shorter than to have something short and work on it to make it longer. Because if you have something short and you work on it to make it longer, you will have to like pull a rabbit out of a hat to make it bigger. So it's usually better. The rule is it's usually if you have an equivalence and a theorem with an equivalence, and you wonder which side should I start on? Well, sometimes they're about the equal length, but if one of them is really really long, and one's really really short, start with the long one and try to simplify it. That's a little.
Wait, for 332,
For 332, yeah, 332 is tricky.
since it has 3
Oh, really?
sides,
Yeah.
can you just choose? Like, if you would do that method, would you just choose the most complicated one? It would be.
Well, or you could choose, or you could choose 2 of them. Like you might choose P or not Q equals P and try to get it to P or Q. Or you might choose P or not Q and try to get it to P or Q equals P.
You can flip it around like that?
Well, at this point now we know that equivalence is what? How do you flip it?
Symmetrical.
Is it associative or is it symmetric that
No,
says P?
symmetrical, yeah.
It's symmetric.
So you can flip it around. And
Yeah, so you could in your head you can just as easily say this is P or not Q equivalence P or Q equals P.
Would you recommend doing it that way?
I have no idea.
I didn't.
I have no
I
idea.
just used the whole thing.
You're just going to have to, yeah.
I've proved this many times to know.
Well, I say I have no idea.
Yeah.
Okay, so this is disjunction. Now, a really cool aspect of this system is how we relate conjunction with disjunction. Now, with disjunction, we had all those axioms, right? But with conjunction, we have just one axiom that describes conjunction in terms of disjunction, and that is called the golden rule. 3.35. Golden rule. The golden rule is do unto others as you would have them do unto you, right? This golden rule, according to our scriptures, is this defines what P and Q is. And it is defined to be P and Q equivales P equivales Q equivales P or Q. All right? And notice it has a nice little symmetry about it. You got P and Q here, you got P or Q here, you got an equivales P and an equivales Q, and this is how they're related. Yeah? And this is the first time in our whole list of theorems and axioms that we have this and. So this is basically is the definition of and. And it's in terms of an operator that we already know its properties from the previous lists. Okay? Is everybody good?
Yeah.
And one of the things that you're going to prove from me for next time is 3.36, symmetry of n. In fact, a couple of you guys already showed me that you did that. And what do you how do you think you should do symmetry of n, 3.36? It says P and Q equals Q and P. Well,
Use the golden rule.
just P and Q, yeah, use a heuristic. You got P and Q, you know that equivales all of this, but then you know that there's some symmetry that you can do with equivales and or, and then you can go back to the golden rule and...
So we can't just say P and Q equivales P or Q.
P and Q does not equivalent P or Q.
Right.
Actually, that is a really good point. Now, let me emphasize what you... why would it be tempting to say P and Q equivales P or Q? Because, I mean, after all, if this equals this and this equals this and this, then doesn't this equal this?
No.
Why not? Because equivales is not... what are the two meanings? What's the difference between equals? You're getting now what you're getting confused.
That,
That,
with binary or Boolean.
yeah, but that's not the main thing.
The one that's equals is not distributive.
No. Distributive is the incorrect word. No.
I'm just going to keep guessing.
Starts with a C. Ferris Bueller. Starts with a C. Ah, look. Equals is equal. Here's what you're getting confused with. Equals is whereas equivales is what? No. No. Starts with an A. Associative. Oh, sorry, I didn't hear you.
You said it about equals. No, you did say that.
Yeah, one of the things you'll find is that I'm getting a little hard of hearing in my old age. So I can always blame it on that. Okay, so equals is conjunctive, equivales is associative. Now look, and what you were thinking was, you were thinking of the conjunctive meaning. Because with the conjunctive meaning, if this was equals, it would be P and Q equals this, and what? It would be P and Q equals P, and what? P equals Q, and what? Q equals P or Q.
Right.
But that's not what equivales, that's not how you can't say that with equivales.
As long as you can just say P equals Q, which doesn't even make any sense. Well, P equals
Yeah. So you, from this you cannot conclude this. And that's a common mistake in the beginning because even though equals and equivales have the same truth table, one has a conjunctive, equals has a conjunctive meaning, but this has an associative meaning.
You can always use the truth table. That's not true.
Yeah, but we've abandoned truth tables.
But we use the truth table to solve the golden rule.
No.
Yeah, it's in the book.
Well, I mean, if you want to do the truth table for all of these, I guarantee you you'll have true in the last column every single time on all the entries. Okay, and now 337
It's a
is the associativity of and you're going to prove for me 3.38, idempotency of and.
That was a strange word.
Look, so not only is, oh, what did we just find out? What did we just learn about idempotency?
It's a weird word.
No. What other operator is idempotent?
Or
Or was idempotent, right?
Yeah.
But now what do we see? What does 3.38 tell us? And is also idempotent.
Those are the only two.
Well, I wonder how we can prove that and is idempotent.
Use the golden rule.
Golden rule.
Probably.
Yes, definitely.
Or you can look in the book and it tells you.
Well, I mean, this tells you that and is idempotent. That is, it's
Well,
one,
it
one,
tells you why.
Who are you gonna believe?
I know, but you have to be able to prove it.
they're supposed to.
So anyway, that's an assignment for the next time
What's
is
the minus isn't idempotent?
to prove it. And now, what did we say the identity element was? What is the identity of multiply?
No idea.
1.
1, because why?
Anything
Because
with 1
x
is
times 1 equals
X.
x. And what's the identity for addition?
0.
Because why? 0. Because why?
1 plus 0.
1 plus, because x plus 0 is
X.
x. And what is the identity for equivalence?
True.
Because why?
X equals true equals X.
Because it's a factor.
Yes, because x equivalence true equivalence x. And what's the identity for, did we have?
Yeah, we did.
Did we have and what's the identity of, oh, I didn't mention this before. What's the identity of or?
False.
False. Because why? False or p equivalents
True. P.
p.
Yeah.
Are you with me?
Wait
Is everybody clear on this concept of identity?
No idea.
What's not to, what don't you get?
I'm kidding.
True or false.
Are you getting it?
Yeah.
Okay. And now what we're seeing is that there is an identity of and. But what's the identity of and? True, because p and true always equals p.
So true.
Right? Are we good? Does everybody see how that works? Okay. And in fact, you will, oh no, I guess I did not assign that. I did not assign 339, the identity of and. But 3.36 I did assign. And, okay, let's see what else we have coming up here. Actually, let's prove the identity. Let's prove 3.39. Where did we leave off? With whom did we leave off?
Me. Finally.
Well, it was me, but Ben took my spot away.
I did. I'm a terrible person. Let's just rub it in.
Okay. How about we do okay, so let's do 3.39. Identity of and, which is
P and true.
p and true equals p. P and. Okay.
Oh, pick me.
All right. So what do you think?
We use the golden rule.
I think we should use the golden rule. Actually, in this particular instance, I think instead of getting one side to the other
We
side,
use both
I
sides.
think we should get the whole side to a previously proved.
Yes.
Yeah.
agreed.
All right. So here's the
That's
proof.
what I was thinking.
And that's because it'd be hard to get something equal to P.
No, I think you could do it the other way, but I think this way is.
This way's easier.
I think this way is a little bit easier because the golden rule has 4 parts to it.
Right.
And we can use 2 of the parts here, and then we'll get the other 2 will fall out.
Yep.
Okay. So proof we'll go p and true equals p. Okay. So Mason, now's your chance. I'm actually going to ask you to say something.
Since P is in
What?
equivalence, P is in the golden rule.
Okay.
we
So
change P and
So what do we,
Rule.
we're using the golden rule.
35.
Okay, so 3.35 with what?
With, I don't know.
Yeah, oh, but here we have to be precise.
I'll take over.
So,
No,
wait,
no,
are you
hold on.
saying- Are you saying you want to use 2 or 1?
With Q replaced by.
Shh, 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 shh. We're asking?
Because I was going to say that.
Okay, come on, come on.
With Q
3.35.
replaced by true.
Okay, with Q replaced by true.
I was asking if you wanted to do it 1 step at a time.
I got you, dude. Don't worry.
Because you could do it 1.
Okay, so now, Mason, then this equals what?
That equals P and true.
No?
Wait, well, actually, no. It equals Q.
No.
No. It equals true equals P or true.
Yes, so it's
Yeah.
Q equivals.
True.
Oh, sorry, you're right, sorry. True. Equivals what?
P or true.
P or true.
Nobody likes extra substitution.
What do you think, Josh?
I do. This is the easy part.
Josh,
Oh, yeah.
what?
We're done.
Well,
Disjunction.
And we have to do the
why are we done?
idempotency
Well, that's it. That's the 0.
or the 0.
We have to symmetricize.
What? Okay, so you want to use you?
Flip it around. Do you really need to go back?
Well, yeah, let's flip it around just for fun.
Okay.
How do we flip it?
Symmetricize.
Okay, so by
Let's try
symmetry,
SYM, that's it, dot. No, you don't need your S.
by symmetry, and so what are we going to make it?
P or true equals true,
And now what do we say?
which is
We cite it.
0 of or, AKA.
Boom, we're done.
3.29.
AKA what?
3.29.
AKA 3.29.
Ha.
You gotta quote me on that.
Are we good?
Mm-hmm. We're golden.
So
How about?
we don't have to write symmetry with P replaced by true.
Well, I mean that really is going.
Can we just write SYN?
Sure. To be strict, you should say symmetry of what?
Symmetry
No, symmetry, not symmetry of and,
equivalence.
symmetry of equivalence.
Is that enough? Like SYM dot equivalence?
Sure,
Yeah.
Sim dot equals.
Sure. sure.
Is there a symmetry of anything else?
Can we just turn it-
Yeah, there's a symmetry of and,
There should be
Symmetry
there's a symmetry of or,
or
Not
symmetry of
equivalence.
not equivalence.
Not equal.
symmetry of not equivalence.
symmetry plus.
Oh, yeah, look at that.
Yeah, look at all those.
Symmetry
Look at all those symmetries.
All about an equivalence.
Okay, let's do 3.42.
Symmetry equals.
3.42, contradiction.
What?
P and not P equivalence false.
Oh, yeah, that's contradiction. That's what it is.
P and not P equivalence false.
Golden rule.
Interesting, isn't it? Because P or not P is true, but P and not P is false.
Can't have something and not.
Have it at the same time, so therefore it has to equivalence false.
So it's true.
But here again, we don't just say Okay. Okay, so here we go. Here's a proof.
That's the proof.
This time let's don't do the whole thing. This time let's start with one side and get it to the other. So which side should we start with? The simple one or the complicated one? The complicated one. Okay, so Ben, I think it's your turn, right? Okay, so we'll go P and not P.
Equivalence false. Let's use.
Let's use, do you have a suggestion?
Yeah, let's use the golden rule.
I think the golden rule is good. 3 point, which was the number is it?
Q replaced by not.
3.5.
3.5. With Q replaced by what?
Not P, but you don't have to put that up.
Q replaced by not P. All right.
Yeah.
Okay, Rochelle, can you tell us what's going to come next if we use the golden rule on this? So the golden rule says P and Q equals all that. So well, if P and Q equivals all that, then P and not P would equivalent what?
P and not P equivalence P equivalence not P equivalence P or not P.
Is everybody starting to get the hang of this now?
Yeah.
She said it just right, right? Are we good? What do you think,
I'm gonna have to think about it.
Kyle?
Disjunction way, huh?
What does this look like?
False. That equals.
Hold on, get your equation sheets out.
I know what the other one looks like.
What is this?
The other bit looks like an excluded.
Yeah.
Oh, this one does look like an excluded middle.
It is.
Oops.
It
Oh,
is an excluded.
aha. So what do you want? Maybe we should do.
Yeah, let's do that.
Okay. So Kyle, what do we? How do we say this?
Excluded middle, P or not P.
Okay, so. So how do we bring this? So what do we do on this next line?
We write just EX mid for that.
That's sufficient. Wow, you're very.
I'm efficient.
Yeah, your questions are following a pattern here. I'm detecting this pattern. That can I use RUP? You loved RUP, didn't you?
I did, that was really
Okay, so let's. So what? How did? Okay, so how? How do we do this? What do we write down next?
P equals not P.
P equals not P equals what?
True.
True.
Add a literal there.
But on the other hand,
Yeah, I don't think do that.
yeah.
We can just kind of get rid of it.
Well, yeah. Let's just do that right now. We could combine these two into one, but for now, let's just. How would we get? What would we do now?
There's a problem.
It's,
How do we get rid of this equals true?
just drop it.
But how do you say? You can say.
Well, not P.
We didn't need to add it in the
3.3.
first place, did we?
Use 3.3.
Yeah, 3.3 is correct.
Because I was going to say 3.15 directly contradicts that statement.
Oh,
Does everybody see how 3.3? That's the identity.
Yeah.
True is the identity of
Yeah, but
equivalence.
Wait, can't you just turn the P equivalence not P into a false? Yeah.
Well, I hope we can because that's what we're trying to get. But how do you? But
Oh, how'd you-
actually, hold on. Okay, Mason, it's your turn. So now what? How do? Because we're trying to get this
I
to
don't see
be.
the 3.3. How'd you get?
Because 3.3. Look at your 3.3 on your equation sheet.
Yeah.
It says true equivals
Q.
Q equivals. So true equivals anything is that thing. So true equivals this is that.
314.
Whoa.
It's 3.3
Oh,
with Q.
okay, yeah.
Are you with me?
With Q replaced by P equivalence.
Exactly. See why sometimes it's worth a while to put down with Q replaced by? But we didn't do it this time because we thought you could do it.
The next step.
Okay, good. All right, now, but Mason,
What you do is just P equals not P equals not P equals not P.
3.15.
You just took it away.
Yeah.
what? No,
Like you took away the
You're
whole
not
right.
basing-
Do the other step first. Turn it into a false first.
I did.
Then do 3.3.
I said it a long
easier.
time ago.
okay, so how do we go, now how do we, 3.15?
Yeah.
Equals false.
Equals false.
Yes, and symmetry, actually. Right?
So why after you do the excluded middle, do you have to make it equivalent to true?
Because I thought 3.15, I thought, because I thought it's not P equivals P, is to get these around like this, right?
Oh, so it be both.
Well, I mean, you probably did, yeah. So this is false. And now, do we quote, is this a previously proved theorem? Yes or no? Do we say which is?
Well, it's just.
No, because we're getting it to the other side. So we can't quote it, because it's not a previous one.
Nice. Good work, team.
Okay, so where you have P equals not P equals true.
Mm-hmm.
I understand you made it you using 3.3 made it P equals not P, but it should be equals P equals not P, right?
No, because we're using 3.3.
Switch around the last two
Look,
steps.
look, we are using 3.3 with, I forget this. What's the letter that they use in?
With Q replaced by P equals not P. Trust me.
Yeah, with. That's my line. Does that make it more clear?
So then we'd have P equivalence not P equivalence
P.
P equivalence not P equivalence P equivalence not P.
Yeah.
Yes.
We would have P equals not P.
And then true would turn into two of those.
That's what I'm confused about.
Switch around the last two steps. It makes it less confusing. Do 315 and turn that.
Yeah, we've done it.
false.
We've done it this way. I don't want to go
False
erasing
equals
and
true.
doing those.
And then you have false equals true, and then
Look,
3.3 with Q
Are you
replaced
saying
by
we can
false.
just
Ben.
use 3.3 to drop the equivalence true?
yes.
Okay.
That's a good way to look at 3.3. Look at what 3.3 says. It says that anytime you have true equivalence anything, that's the same thing as the anything.
No, yeah, it makes sense.
So true equivalence this is that by 3.3.
I actually prefer this. I'm glad that works. Before I was like, I always had to make it two of the same thing, and it was really disaster.
But you understand that this is the meaning of 3, this is how we can use 3.3. Anytime we have an equivalence true, we can drop it by
We
3.3.
basically just said that true equivalence
Anything that equals
Q
true is true. so
is
it's
Q.
Yes,
That's
yes,
exactly what we did.
that's exactly what we did.
But what I don't understand is how could that statement equal true and then it equals false?
No. We're getting, because we're starting with one side and we're getting it to the other side.
No, he's saying
I'm
okay,
saying-
P equivalence not P equivalence true, and then that also equivalence false.
Well, it doesn't.
The whole.
It doesn't.
Well, the whole, hold on. This whole thing equals this. This whole thing also does equivalent false. This whole thing does equivalent false.
Yes.
I like that better.
Are you with me?
Yeah.
Because by the way, we are using transitivity.
Just because you have an equivalence true on the end doesn't mean the whole.
Doesn't mean that this part is true.
Yeah.
Right.
Well, because this whole thing that we're dealing with is not a theorem. This is the left-hand side of an equivalence. Do you understand what I'm saying? That maybe that's what was confusing. Before we were starting, if we were starting with the whole theorem, with the whole theorem and trying to get it to a previously proved one, then every step along the way with the equals would be a theorem.
Yeah.
But now it's part of it. So yeah, that's a good observation. That's good insight.
It's just trying.
Yeah. No, that's a really very good point. That's good insight. Good insight.
Sweet.
All right. So now I will leave you with this. The other two, these are going to be hard. De Morgan. Oh, have you already done it? You think it was easy? Okay. So De Morgan A says not P and Q equivalents not P or not Q.
Yeah.
Now that one, I've given you some extensive hints so check out the hints. If you don't, that's fine with me. But trust me,
All right. You want to use this hint?
I mean that's for your own good. The hints are not like hints are not like supplementary exercises.
Okay.
They are optional. But if you know what's good for you, eat your broccoli, eat your spinach, and grow up like Popeye. Okay. And the other one, B,
You have to eat a lot of
is not P or Q equivalents not P and not Q. So both of those are also on the assignment for next time.
concentrated spinach.
This is like concentrated
No, we
spinach.
should make it because you have to eat a lot of spinach to get enough nutrients.
And the other thing that makes it like spinach is it's good for you. Because you know what we're learning how to do? We are learning how to think.
That is useful.
And that is useful.
I get it.
All right.
I have a question.
See you next time.
Off